The moon is currently empty. 12 people have stood on that surface in all of human history, and every one of them left within 3 days. Getting there was never the hard part. Visiting is solved. Living there is a different problem entirely. A home is not a shelter. It is a machine. Every single thing that keeps a body alive down here, the air, the water, the warmth, has to be manufactured up there and never allowed to stop. Switch it off and you have about 15 seconds of consciousness left. By the end of tonight, you'll know why that machine cannot hold, and why the moon will let us visit forever and never let us stay. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It helps this channel reach more curious minds like yours. Now, let's begin. That absence up there is not a failure of rockets, or of money, or of nerve. The moon does not weather anything. There is no rain to rust a hinge, no wind to bend a panel, no air to carry rot. By every instinct we have, that should make it the easiest place in the solar system to build something that lasts. It is the opposite, and the reason why is not the one most people would guess. We have been watching that surface for far longer than we have been able to reach it. The moon has held a place in human attention since before anyone thought to write anything down. Ancient civilizations tracked its changing face to time their planting and their festivals. Poets wrote about it. The first people to point a telescope at the sky studied its craters and named the dark patches seas, mistaking shadow for water. For most of that history, the moon stayed exactly what it had always been. Not a place, a boundary. The edge between earth and heaven, close enough to watch every night and far enough to never touch. Then, on July 20th, 1969, that boundary broke. Neil Armstrong pressed his boot into the loose grey soil of the lunar surface, and the unreachable became a destination. It felt, at the time, like the opening move in something much larger. Bases would follow, then outposts, then, eventually, cities. Grandchildren would be born under a black lunar sky, looking up at the blue marble of Earth, the way we look up at the moon. That did not happen. More than 50 years later, humans have not gone back. The last bootprint in the lunar dust belongs to Eugene Cernan, who climbed into his lunar module in December 1972 and left the surface untouched ever since. Footprints, flags, 50 years of silence. But the silence is ending. Plans are underway again, and this time they carry real weight behind them. A lunar gateway space station is being built as a waypoint for surface missions, with modules and expertise contributed by the European Space Agency, the Japanese Aerospace Exploration Agency, and the Canadian Space Agency. China's National Space Administration has already landed its own rovers on the surface and carried samples home through its Chang'e program, and its officials now speak openly about permanent bases at the lunar South Pole. Private companies have joined the effort too. SpaceX is building Starship, a vehicle designed to eventually carry 100 passengers toward Mars. Dozens of smaller companies are developing suits, habitat modules, mining equipment. Billions of dollars are funding blueprints of pressurized rooms, tunnels, hydroponic gardens lit by artificial sunlight, and windows built to frame a view of home. The promise underneath all of it is the same one from 1969. A species that evolved on a single world becomes a species that lives on several. The moon, in this telling, is a stepping stone to the stars. The people building toward that promise are not amateurs. They are, by any honest measure, among the most capable engineers alive. They have landed robotic probes on comets tumbling through space at 40,000 miles an hour, roughly 60 times the speed of a car on a highway. They have photographed the shadow of a black hole 27 million trillion miles away, a distance so far beyond ordinary experience that no amount of driving, flying, or sailing across the whole of human history would ever cover it. They have kept astronauts alive in low Earth orbit continuously for more than 2 decades. These are people who bend physics to human will through mathematics, materials, and patience. And yet, there is a problem they have not solved. Not incompetence, not underfunding, not a lack of nerve to try again until it works. The problem sits underneath all of that, in a place no amount of cleverness can reach. Every plan for a permanent lunar settlement depends on something called closed-loop life support. In plain terms, that means machines doing artificially and without rest, what a living planet does for free. They recycle the air so it stays breathable. They purify water so it stays drinkable. They regulate temperature and manage waste, holding a small bubble of survival conditions inside an environment that offers a human body nothing at all. It is an artificial ecosystem, built from pumps, filters, membranes, and seals, standing in for the one Earth provides without anyone ever having to ask for it. And here is the problem no one has budgeted for. Closed-loop life support systems degrade faster than they can be maintained. Not occasionally, not under unusual strain. Every time, everywhere the idea has been tested. This is not a temporary gap waiting on a clever fix, the way a flawed part waits on a better design. It is a basic feature of complex mechanical and chemical systems running inside a hostile environment. And the moon may be the most hostile environment human beings have ever seriously tried to live inside. That is the claim the rest of this argument is going to test, from every direction it can be tested from. Not the intelligence of the engineers building toward it, not the ambition of the governments and companies funding it, just the one machine everything else depends on, and how long it can actually be made to hold. To see why that degradation is fatal rather than merely inconvenient, start with the one number that governs everything: how far away help actually is. On the International Space Station, life support works reasonably well. Not because the machines up there are better than anything a lunar base would carry, because the station orbits just 400 kilometers above the ground, close enough that Earth fills half the sky out every window. When a filter clogs, a pump fails, or contamination builds up faster than the scrubbers can pull it out, resupply is never far behind. Cargo vehicles launch from Florida, from Kazakhstan, from Japan. Each one carries spares, fresh water, replacement hardware, whatever the station's engineers on the ground have flagged as running low that month. A broken component gets swapped out within days. A struggling system gets upgraded before it ever becomes a crisis. This has become so routine that it barely registers as remarkable anymore. A truck arriving on schedule again and again for more than 2 decades running. The pipeline from Earth never really stops. And that is the part worth sitting with. It means the station's closed loop is closed in name only. It leaks constantly, in 100 small ways, and Earth quietly reopens it every few days without anyone on board having to think twice about it. The astronauts call it a closed-loop system in the mission briefings. What actually keeps them alive is an open one, propped open by a planet with the infrastructure to keep propping it open indefinitely. The moon does not get that gift. The moon sits 384,000 kilometers away, roughly 250,000 miles, nearly 1,000 times farther than the space station. A resupply mission, under the best possible circumstances, takes 3 days at an absolute minimum, and that number assumes something that does not currently exist anywhere on Earth. A fully fueled rocket, already stacked, already sitting on a launch pad, ready to fly the moment it is needed. No such rocket sits waiting, not for a lunar base, not yet. In practice, an emergency resupply would take weeks to prepare, more likely months, once a vehicle is built, fueled, tested, and cleared to fly. And that estimate assumes Earth's own launch infrastructure is working perfectly at the exact moment it is called on, weather cooperating, no technical hold, no funding delay, which it very often is not. Distance does more than slow down the mail. It removes the safety net that every other form of human spaceflight has quietly relied on since the very beginning. There is no warehouse of spare parts sitting a short drive away. There is no window to crack open for a breath of fresh air, because there is no air outside a lunar habitat to let in, only vacuum. There is no neighbor to borrow a part from, no hardware store to walk to for a replacement gasket or a filter cartridge, because the nearest one is 250,000 miles behind a wall of hard vacuum, with nothing in between to carry it across. Here is what that means in practice, stripped of any softening. If a carbon dioxide scrubber fails at 3 in the morning, on a base where a handful of people are asleep, and no rescue vehicle is within days of arriving, there are exactly 2 outcomes available. Fix it, with whatever tools and materials happen to already be on hand, or suffocate. That is not hyperbole, and it is not pessimism dressed up as drama. It is engineering reality, stated as plainly as it can be stated. No amount of training changes this equation. No amount of caution built into the design changes it either. A well-trained crew with a well-designed scrubber still needs the one part they did not think to bring, or the one tool that broke the week before, and at that point, training and design have both already done everything they can do. What is left is whatever sits in the storage racks of that specific habitat on that specific night, 250,000 miles from anyone who could hand them something better. On the space station, a failure like that is a bad night and a line in a maintenance log. On the moon, the same failure is not a delay to be logged and scheduled around. It is a choice between repairing a machine in the dark and running out of breathable air before anyone can help. Not an inconvenience anymore. Not a delay. A verdict. That difference is the whole of the problem, compressed into a single fact about geography. A system that merely needs to fail rarely, which is the standard every engineer on Earth quietly designs toward, and which the space station meets comfortably with its resupply pipeline intact, stops being good enough the moment the pipeline disappears. On the moon, rare failure is not an acceptable target. The standard has to be no failure at all, sustained indefinitely by machines that were never built anywhere, by anyone, to run indefinitely without a delivery truck eventually showing up. It helps to name what is actually being taken away, because the same thing gets taken away again and again as this argument goes on. Earth gives a spacecraft in low orbit a resupply pipeline for free, a whole planetary industrial base standing by, ready to build a replacement part and put it on a rocket within days. Nobody on the space station has to think about where that capability comes from. It is simply there, the way air is simply there for someone standing in a field. The moon strips that particular gift away first, before it strips away anything else. No more free rescue, no more quiet reopening of the loop every few days. Whatever a lunar base carries with it, or can build with its own hands out of its own materials, is what it has. Nothing more arrives unless someone on Earth spends months making it arrive. And that is the standard nothing built so far has ever had to meet. Meeting that standard means holding against forces that never clock out. Two of them start working the moment a habitat is sealed, and neither one ever stops for the length of a human lifetime. The first is emptiness itself. The moon does not have weather, or wind, or breathable air, because it does not really have an atmosphere at all. There are trace gases drifting near the surface, helium and argon left over from the slow decay of lunar rock, hydrogen and oxygen blown in on the solar wind, but the total pressure they add up to is close enough to nothing that engineers round it down to zero, a little over 1/4,000,000th of a single atmosphere. Put a thermometer and a barometer on the lunar surface, and the barometer might as well not be there. Step outside a hab without a suit, and the air already in your lungs, and your blood would not slowly seep away. It would rush outward, hard, toward the emptiness, the way water rushes toward a drain the instant a plug comes loose. On Earth, none of this is a design problem at all. The atmosphere presses back on every wall and window, with almost exactly the same force pushing out from inside a building. So nothing has to fight to hold its shape. That balance is not something engineers build. It is something the planet supplies, quietly, for free, everywhere at once, to every structure ever built. The moon offers no such balance. Whatever holds the line between breathable air and hard vacuum has to be built, sealed, and maintained by hand. And it has to do the job the atmosphere back home has always done without being asked. That is what any lunar habitat has to hold back, all day, every day, for as long as anyone lives inside it. Ordinary sea level air pressure works out to about 14.5 pounds, pushing on every square inch. Spread that over a single square foot of hull, and it comes to more than a ton, pressing outward, all the time, against the wall, the window, the hatch, every seam where a pipe or a wire crosses from inside to outside. Not for a launch, not for an afternoon, for decades. Imagine parking a small car on its side against every square foot of the habitat wall and asking the wall to hold that weight back forever, without ever setting it down. Every hatch a crew opens and closes is under that load. Every window they look at Earth through is under that load. Every port where a cable or a coolant line passes from the living space to the outside is under that load, all of it. continuously, whether anyone on board is thinking about it or not. Nothing holds a load like that without cost. Metal exposed to constant outward stress develops cracks too small to see with the naked eye. Rubber and plastic seals lose their spring, the give that lets them press tight against a frame. A gasket that fit perfectly on installation day drifts almost invisibly as the material underneath it shifts. The vacuum does not attack in a single dramatic moment. It just never lets go. And vacuum is only the first attacker. The second is heat, or the total absence of it, and the two take turns. A day on the moon runs about 2 weeks, and for that entire stretch the sun beats down with nothing overhead to filter it. No clouds, no blue sky scattering the light into something gentler, no layer of air to soak up any of the intensity before it reaches the ground. Surface temperatures climb to 127 degrees Celsius, hot enough to boil water sitting in an open pan, hot enough to soften certain plastics and swell metal components measurably larger than their design specs. Then, the 2-week night arrives, and there is nothing left to hold the warmth in. Temperatures fall to 173 degrees below zero, colder than anywhere on Earth, colder even than the surface of Mars, cold enough to turn ordinary lubricant into something closer to wax, cold enough to make steel forget how to bend and start cracking instead. A 300-degree swing every 29 days. For as long as the base exists, different materials expand and shrink at different rates, and that mismatch is where the real damage lives. Picture a rubber gasket sealing the lid of a jar, except the jar is made of one material and the lid of another, and every month, the whole assembly is baked, then frozen, then baked again. Each cycle, the seal presses a little differently against its frame than it did the cycle before. Microscopic gaps open, they close, they open again, a little wider this time. Do that enough times, and the rubber stops springing back to its original shape at all. Engineers call it taking a permanent set, a stiffening that never reverses. Eventually, somewhere along that hardened, tired seal, a crack opens that never fully closes again. It does not need to be a large crack. Gas molecules are small enough to find their way through an opening no eye could spot. The obvious answer sounds simple. Build it out of something tougher. Engineer a material this environment cannot touch. Not a material that ignores 300 degrees of swing every 29 days. There is no such material. Specialized alloys outlast ordinary metal. Advanced polymers outlast rubber. Ceramic composites, built to shrug off heat that would melt most materials, outlast both. But better is not the same as immune. Not one of them survives that cycling forever. Every single one of them, alloy, polymer, ceramic, only fails more slowly than the one before it. The clock still runs. It just runs a little longer before it stops. And the crack, once it starts, is patient. It does not need to be large. It does not need to be sudden. It only needs time. And on the moon, time is the one thing every seal is guaranteed to get. Vacuum and heat are not the only forces working, unseen, against every boundary a habitat depends on. They are only the first two. Vacuum and heat are the two attackers a habitat can at least see coming, in the sense that engineers can calculate them, test against them, budget for their slow damage. The third attacker arrives from somewhere else entirely. It does not come from the ground underfoot or the temperature swinging overhead. It comes from deep space. It never stops arriving, and no seal, however carefully engineered, has ever kept it out. On Earth, this threat mostly never reaches you. The planet's magnetic field extends tens of thousands of kilometers outward, a magnetic bubble wrapped around the whole world roughly the way the equator wraps around it, several times over. Charged particles from the sun and from deep space hit that field and get deflected or trapped in vast belts far above the surface, long before they reach anyone standing on the ground. What does slip through gets caught by the atmosphere, converted from a dangerous high-energy particle into a harmless cascade of weaker ones by the time it reaches sea level. Billions of years of evolution happened under that double shield. Nobody had to build it. Nobody has to maintain it. It has simply always been there. The moon has neither. It has no atmosphere to soften anything. It has no meaningful magnetic field, just a faint trace left behind by a core that finished cooling billions of years ago. It has nothing standing between the surface and space. Every particle a distant sun or a distant supernova ever throws off arrives at the surface exactly as violent as it left. Unfiltered, unslowed, unstopped. Think about what that actually means for a habitat sitting exposed on open ground. Every hour of every day, the surface is being struck by particles that Earth quietly absorbs before anyone below ever notices. On Earth, that filtering happens continuously, silently, as part of just standing on the planet. On the Moon, whatever standing there is left to do, the body does unprotected. Some of what arrives is almost impossible to picture. Galactic cosmic rays are not simple particles drifting through the dark. They are atomic nuclei, often iron or something heavier, accelerated to nearly the speed of light. The same kind of object sitting in the core of a coin, fired out of the universe's most violent explosions, and crossing the galaxy at a speed nothing built on Earth has ever matched. When one of these hits solid material, it does not stop at the surface. It punches deep, and along the way it shatters atoms in its path, throwing off a spray of secondary particles behind it. That single fact creates a strange problem. Building a thicker wall should help. It does not always help, but here's where it gets strange. Shield a habitat with the wrong material, especially something dense like lead or heavy steel, and the shielding itself becomes a source of danger. The incoming nucleus slams into all that dense material and sprays secondary particles through it, and in some configurations, more of the wall means more of the spray reaching the people inside. Not thicker shielding, not better protection. In the wrong material, more shielding can mean more radiation. Water and ordinary plastic, being rich in hydrogen, absorb the impact without throwing off nearly as much debris, which is why they turn out to be better shields than metal ever could, despite feeling flimsy by comparison. The steady background of cosmic rays is only the chronic threat. There is an acute one too. The sun periodically erupts, hurling a cloud of high-energy protons outward in what is called a coronal mass ejection, and that cloud can reach the moon within minutes to a few hours. A large enough eruption, arriving while someone is outside a shielded habitat, could deliver a lethal dose in a matter of hours. There is little warning and less time to react once the cloud is already on its way. Shielding helps, but only ever part way. Water tanks positioned around a sleeping area block a meaningful share of the dose. Ordinary plastic panels do the same. Even the loose rock and dust covering the ground, piled thick enough over a buried shelter, blocks a real portion of what would otherwise get through. None of them block all of it. No practical combination of materials, however cleverly arranged, brings the number down to zero. Whatever gets through adds to a running total that only ever climbs, day after day, for as long as anyone stays. None of this announces itself. The body absorbs it in silence. Cells suffer damage constantly, on Earth as well as here, and the body's ordinary repair processes fix most of it. Most, not all. Errors slip through the repair process and accumulate, one on top of the last, year after year. The measurable consequences show up later. Elevated cancer risk, cataracts forming earlier than they should, a higher chance of cardiovascular disease. And there is a subtler cost, one scientist can describe only in outline. Nobody yet fully understands what sustained exposure to these heavy, fast particles does to the brain and nervous system over years. That uncertainty is not a gap waiting to be filled by more careful modeling. It is a real and current unknown. The machines suffer their own version of the same slow injury. A stray particle passing through a memory chip can flip a single bit, quietly corrupting a number the life support computer was relying on. Radiation gradually degrades the semiconductor junctions inside every processor, and over time that raises internal resistance and drags down performance in ways an engineer only notices as unexplained inefficiency. Solar panels lose a measurable fraction of their output the same way, cell by cell, as the particles chip away at material never designed to face this bombardment for years without pause. The computers keeping the air breathable and the water drinkable grow less dependable at exactly the pace the mission most needs them to hold steady. Nothing about any of this is visible while it happens. No alarm sounds when a cosmic ray passes through a crew member's chest, or through a circuit board buried behind a wall panel. The damage from this third attacker does its work in complete silence, adding up quietly beneath everything else already fighting to fail, and the full weight of that reckoning in bodies and in years has not even been counted yet. Not every threat on the moon has to travel from deep space to do harm. The fourth attacker in this catalogue never left. It has been sitting on the ground the whole time, underneath every bootprint, waiting. Scientists call it regolith. It is tempting to call it soil, but soil is the wrong word entirely. Soil implies rain, wind, roots, decades of biology working a surface into something soft. None of that ever happened here. Lunar regolith is pulverized rock, the accumulated wreckage of 4 billion years of meteorite impacts, longer than complex life has existed back on Earth. Every particle in it was made by violence. A micrometeorite strikes the surface at tens of kilometers a second, several times faster than a rifle bullet leaves the barrel, and the heat of that impact melts stone on contact. The molten droplets solidify instantly in vacuum. No air to slow the cooling, no water to round the edges afterward. Look at a grain of ordinary beach sand under a microscope, and the edges are rounded, softened by years of tumbling through water and wind before it ever settled on a shore. Look at a grain of lunar regolith the same way, and the picture is completely different. Under a microscope, the result looks like shattered glass. That is essentially what it is. Sharp, jagged, every grain a tiny blade that has never been worn down by anything. And it clings. Without an atmosphere to carry a charge away, solar wind and ultraviolet light build up static directly on every exposed grain, and that charge does not discharge on its own. Static cling on Earth is a mild household annoyance, a sock stuck to a shirt fresh out of the dryer, gone with a single shake. On the moon, there is no shake that works, no breeze to carry the charge off, no humidity in the air to bleed it away, no easy path to ground. The charge simply stays, and the dust stays with it. Dust does not sit passively on a surface the way sand does on a beach towel. It grabs on. Apollo crews learned this the hard way. Dust clung to their suits no matter how thoroughly they brushed it off before climbing back inside. It rode in through the airlock on boots, gloves, tool bags. It scratched helmet visors until visibility degraded. It jammed hinges and latches that had worked flawlessly through every ground test on Earth. Engineers had run those same mechanisms through vacuum chambers for months beforehand. None of those chambers had regolith in them. It got into eyes and throats within hours of exposure, on missions that lasted only days. One of those astronauts was Harrison Schmitt, the lunar module pilot on Apollo 17, and the only trained geologist ever to walk on the moon. If anyone should have shrugged off a little dust, it was him. He had trained for years, studied rock under every condition science could simulate, and stood on the surface calm and unbothered. Wait. Within hours of returning to the cabin, he was congested, eyes watering, describing something close to hay fever. Not irritation from grit in the air, a reaction. His body was responding to a substance no human immune system had ever met. The symptoms passed within days, once he was back in a dust-free environment. But a trained, physically fit astronaut reduced to a congested nose and streaming eyes by a few hours of exposure was not something anyone could dismiss as coincidence. The reason is not mechanical, it is chemical. Regolith carries nanoscale particles of silica glass, small enough to travel deep into lung tissue, well past the point where the human respiratory system knows how to stop them. Left unchecked over months, that kind of exposure resembles silicosis, the disease that scarred the lungs of coal miners and stonecutters for generations, tissue slowly stiffening until breathing itself becomes labor. The same dust also carries iron and titanium oxides, and those generate reactive oxygen species the moment they touch living tissue, breaking down cell membranes and damaging DNA directly. This is not a lung irritant to be filtered out and forgotten. It is not simply gritty or unpleasant. It is toxic, in the plain clinical sense of that word, and it damages the body at the cellular level on contact. Keeping it outside sounds simple enough. It is not possible. Every airlock cycle admits some. Because the outer door opens, dust settles inside the chamber, and crews step through carrying more of it on suits and tools and equipment. Every returning suit comes back impregnated at the joints and seals. Cleaning protocols remove the bulk of it, the visible layer, but the finest particles, the micron and nanometer scale grains, pass through every brush and every filter designed to catch them. There is no seal built by anyone that excludes particles that small. Not a tighter gasket. Not a better airlock design. The physics of the grain size defeats the physics of the seal. So it accumulates. Month after month, year after year, it works its way into everything a habitat depends on. It clogs air filters faster than engineers on the ground ever modelled. It gets into the pumps and membranes of water recycling systems. Abrasive grit doing slow damage to machinery built for clean fluid. It shorts electrical connections and degrades circuit boards it was never meant to touch. It grinds into the same seals already fatigued by vacuum and by temperature swings, wearing them from the inside as well as the outside. Industrial clean rooms on Earth achieve real purity, but only through massive filtration inside a controlled, benign environment that never has to open a door onto a hostile world. A lunar habitat cannot be that. Astronauts have to go outside, work the surface, and come back in over and over for as long as anyone lives there. The International Space Station never faces any of this. Low Earth orbit is a clean vacuum. There is no ground to kick up, no regolith drifting in on a boot. That single difference, ground versus no ground, is the whole reason the ISS has never had to solve a problem the moon creates by simply existing. 4 attackers now stand fully named. Vacuum pulling outward on every seal. Heat and cold, tearing at every joint. Radiation arriving unblocked from beyond the sky. And now dust, already inside the very machines meant to keep the air breathable and the water clean, working against them before those machines have even had the chance to fail on their own. Even without a single grain of that dust working its way inside, the machines built to keep a lunar habitat breathing and drinking would still be losing a fight nobody sees happening. It helps to understand why, because the reasons have nothing to do with dust at all. Call it a closed loop. Water gets purified and used again. Air gets scrubbed of the carbon dioxide a body exhales and refilled with oxygen, rather than vented into space and replaced from a tank. Waste gets processed back into something the crew can use. The entire point of building it this way is to need less from Earth, since resupply is expensive, slow, and never fully reliable. And on paper, every version of this plan looks beautiful. Engineers write out consumables per day, the recycling efficiency of each stage, the equilibrium point where what comes out balances what goes in, and the numbers close. Outputs match inputs. The loop mathematically seals shut. Here is what the math misses. Every recycling process is imperfect. Every filter lets something through. Every chemical reaction leaves behind a trace byproduct. Every mechanical part wears, however slightly, with each cycle it completes. Start with air. The job is simple to state. Remove the carbon dioxide a body breathes out, and put oxygen back in its place. The method engineers trust most right now is called the Sabatier process, named for the chemist who first combined carbon dioxide with hydrogen to produce methane and water. That water then gets split, or electrolyzed, into oxygen and hydrogen, and the hydrogen goes back into the reaction to start again. On paper it looks closed. Carbon dioxide goes in. Oxygen comes out. The only leftover is methane, vented outside or stored as fuel. Nothing about that reaction runs on hope alone. It needs a catalyst, usually nickel or ruthenium, a substance that speeds the chemistry along without being used up by it. That is the theory. In practice, it is used up, slowly. Trace contaminants settle onto the catalyst surface and poison it, and as it fouls, efficiency drops. Engineers raise the temperature to compensate, and the higher temperature accelerates the very degradation they were trying to outrun. Push a machine harder to make up for its own decline, and the pushing becomes part of the decline. The electrolysis side fails in its own way. The cells corrode. The electrodes collect mineral deposits the way a kettle collects a crust of scale after years of boiling the same water, layer building on layer until the element beneath struggles to do its job. And the membrane, meant to keep hydrogen on one side and oxygen on the other, develops microscopic holes, letting the two mix where they should never meet. Efficiency drops, power use climbs. None of these are dramatic failures. No alarm sounds the day a catalyst loses 2% of its capacity. The habitat simply produces slightly less oxygen than it did the year before, and slightly less again the year after that. Where do the contaminants come from? A crew, mostly. A body breathes out more than carbon dioxide. Sweat contributes ammonia, digestion contributes sulfur compounds, and even the walls contribute, slowly releasing formaldehyde from the materials used to build them. Add in whatever dust has already worked its way inside from the airlock, and the chemistry is fighting contamination from every direction at once. Not once, every month, every year. The system converts a little less carbon dioxide into a little less oxygen, and asks for more maintenance to keep doing even that much. Not a system that closes and stays closed. A system that closes for a while, and leaks a little more with every cycle it completes. Water suffers a version of the same problem, only slower to show itself. Recycled water has to lose its organic compounds, its dissolved solids, its biological contaminants, through filtration, through distillation, through chemical treatment. Each stage catches most of what passes through it. Not all. The residue that survives one stage moves on to trouble the next. Biofilms are the quiet colonizers. Despite antimicrobial treatment, thin communities of microbes take hold inside pipes and reservoirs anyway, adapting, finding a crevice the chemistry missed, and settling in for good. They are remarkably difficult to kill outright, since a colony that survives one treatment often comes back more resistant to the next. Minerals do their own version of the same thing. Calcium, magnesium, and other dissolved solids drop out of solution the way sediment settles at the bottom of a glass of tap water, left too long on a counter. Except here it never gets poured out. It clogs valves. It coats heating elements and cuts their efficiency. It lines membranes and narrows the passages meant to let clean water through. Two separate degradations, chemical and biological, working the same pipes at the same time, neither one waiting for the other to finish. None of this is theoretical. On the International Space Station, these exact systems need constant attention. Astronauts spend hours every week keeping air and water recycling equipment running, swapping filters, flushing lines, replacing a part before it fails outright rather than after. And when a component does finally fail, a replacement launches from Earth and arrives within a matter of weeks. That timeline works because the station orbits close enough for it to work. A failed carbon dioxide scrubber on the moon does not get that grace period. There is no replacement in weeks. There is only what is already degraded, still running, a little worse than it ran the month before, with nobody able to swap it out before it gets worse still. This is the same shape as the claim made at the very start. Closed-loop life support degrades faster than it can be maintained. It was true for the seals working loose under vacuum. It was true for the joints cracking under 300 degrees of swing. It is true, too, for the chemistry meant to keep a crew alive. Catalyst poisoning, membranes leaking, biofilms colonizing, scale building, one invisible fraction of a percent at a time. Earth performs this same chemistry for free. An atmosphere that already holds oxygen, rain that already falls clean, a planet's worth of biology quietly finishing the filtering no lunar machine will ever finish alone. None of this is a reason to stop building the machines. It is a reason to ask what happens next, when the parts wear past what cleaning and adjustment can fix, and someone has to replace them using only what already made the trip. The obvious answer is to bring plenty of spares, build redundancy into every critical system, and train the crew to fix almost anything without waiting on a phone call to Earth. All of that helps. None of it solves the problem underneath. Start with the spares themselves. A cargo mission to the moon might deliver a few tons of payload, roughly what a couple of loaded pickup trucks could carry, and a good share of that has to be food and water before a single spare part gets loaded. What is left has to cover a habitat with thousands of components, and no manifest can include everything. First, you cannot bring infinite spares. Mass is the ceiling, and food and water claim it before parts do. Second, you cannot anticipate every way a system can fail. Designers test for the failures they can imagine, running components through every stress they can think to simulate on Earth. The moon supplies failures nobody imagined, combinations of stresses that only appear after years of vacuum, dust, and thermal cycling acting on the same part at once, in a sequence no test bench ever reproduced. Third, you cannot always repair what has already degraded past the materials on hand. A pump with a worn bearing is a simple fix, if you happen to have carried the right bearing. But what if the housing around it has cracked? What if the motor windings have quietly degraded from radiation? What if the seal has taken a permanent set from months of thermal swing that no spare in the inventory was ever cut to match? 3 different ways for a fix to run out of road, and any one of them is enough. And repair carries its own cost. Replace a seal, and you may shift the alignment of the joint it sits in. Swap a filter, and you may introduce a trace contaminant the old one had already been fighting. Adjust a pump, and you may put new stress on whatever it connects to next. Fixing one thing quietly opens the door to fixing another. Something else was happening. None of this is incompetence. It is thermodynamics, the physical law that says organized systems left alone drift toward disorder. The way a garden left untended fills with weeds, not because anyone intends it, but because that is simply what happens to anything complex when nothing keeps working against the drift. On Earth, we fight that drift constantly, without ever noticing the fight. A part fails, and a technician is called. A component is missing, and it ships from another continent by morning. A specialist retires, and a supplier somewhere has already trained a replacement. Behind every routine repair stands an entire planetary industrial civilization. Mines, foundries, factories, shipping lanes, quietly manufacturing low entropy order and handing it to you the moment you need it, at a scale so large that nobody living inside it ever has to think about where the order comes from. On the moon, you are the technician. Your spares are whatever you brought, or whatever you can build from local material, using equipment that is degrading at the same time you're trying to use it. Not a smaller version of Earth's safety net. No net at all. Here is where the natural next idea seems to rescue the argument. If Earth cannot keep resupplying you, build what you need on site. Mine oxygen out of the regolith. Pull water from the ice, sitting in the permanently shadowed craters. Process local material into replacement parts, and cut the cord to Earth almost entirely. It sounds like an escape from the whole problem. It is not an escape. It is the same closed loop, grown larger. The equipment that mines and processes lunar material wears against the same abrasive, glass-sharp dust, already fouling every other system on the base. The processing plants need their own maintenance. The electronics that control them take the same radiation damage as everything else. Regolith does hold usable metal, aluminum, titanium, iron, all genuinely there for the taking. But refining raw rock into a working part needs industrial processes that themselves need equipment, energy, and consumables, and modern manufacturing leans on materials the moon simply does not have. Specialized alloys need precise elemental recipes. Electronics need rare earth elements. Lubricants need exact formulations. The more sophisticated the part you're trying to build, the longer the list of things you cannot mine locally to build it. Not a way around the closed loop. A bigger version of the same loop, with more places for it to leak. There is a knowledge problem sitting underneath the material one. A single piece of modern industrial equipment is typically assembled from a supply chain running through thousands of specialized components made by hundreds of different suppliers, each holding one narrow piece of expertise that took years to build. No crew, however well-trained, however many disciplines they studied before launch, carries all of that expertise in a handful of people. Lunar manufacturing can help. It cannot make a small outpost self-sufficient. And that produces the maintenance paradox sitting at the center of the whole question. The tools you would need to maintain your systems need maintenance of their own, and every added layer of redundancy needs its own layer of support standing behind it. Add enough layers, and eventually you run out of layers to add. Nobody runs out of layers on Earth, because the next layer is always a phone call and a cargo flight away. So what does the timeline actually allow? The Artemis program, the current effort to return astronauts to the moon, envisions surface stays measured first in days, then in weeks, building slowly towards something longer. For a stay measured in days or weeks, you can simply bring everything you need and leave before anything degrades enough to matter. Missions measured in months are harder, but they are possible, at a real cost in supplies, spares, and redundancy carried along for the ride. Permanent habitation is a different claim entirely. Cities on the moon, generations born there and living out full lives there, require closed-loop systems that hold not for months, but for decades. Nothing built today, and nothing on any credible drawing board, closes that loop for decades. And of everything that degrades on that longer timescale, one kind of component gathers more of the risk than any other. Not the pumps, not the catalysts, not the electronics quietly losing capacity behind a panel. A boundary holding breathable air on one side and hard vacuum on the other, often no larger than a hand can span, asked to do that job perfectly, for years, without ever once being allowed to fail. History already holds one lesson in exactly what happens when a boundary like that fails. In 1986, the Space Shuttle Challenger broke apart, 73 seconds after launch. All 7 crew died. The cause was not the engines, not the fuel, not any of the great systems built to carry astronauts to orbit. The cause was a rubber ring, smaller than a dinner plate, wrapped around a joint in one of the solid rocket boosters. In cold January air, that ring stiffened. It could not seal the way it was built to seal. Hot gas burned through the gap it left, and the vehicle came apart in the sky. 7 people died because a rubber ring got stiff in the cold. A component small enough to hold in 2 hands decided the outcome of the entire mission. That is the lesson SEALs carry, whether anyone building a lunar habitat wants to hear it or not. A SEAL is at once the most critical component in any pressurized system, and the most vulnerable. It is the boundary between breathable air and nothing at all, between life and death, drawn in a strip of rubber or metal a few millimeters wide. And by its nature, that boundary is destined to fail. Not someday, maybe. Eventually, certainly. The O-ring on Challenger had it easy compared to what a lunar SEAL has to survive. It sat inside Earth's atmosphere, shielded from the worst of space. It faced a temperature swing of tens of degrees, not hundreds. Its pressure cycle lasted minutes, the span of a single launch, and then its work was finished. A SEAL on the moon does not get a single launch. It gets years, decades, if the habitat is meant to be permanent, and it has to hold, perfectly, every one of those days, through cycle after cycle that no engineer testing an O-ring in a Florida hangar ever had reason to imagine. A permanent lunar habitat needs SEALs almost everywhere, hundreds of them, perhaps thousands, roughly as many as a large apartment building has doors, windows, and pipe fittings combined. Every hatch needs one. Every window, every place a pipe or a wire passes through the hole, every structural joint, every module connection. Each one has to hold air in and vacuum out, without exception, for as long as anyone is living behind it. Do the arithmetic and the scale of the risk comes into focus. Give each of 1,000 SEALs a 99% chance of holding over a given stretch, already an optimistic number for anything under continuous cycling. 99% success on 1,000 SEALs still means 10 failures. 10 breaches. Sitting inside components most people would never think to worry about. The mechanism doing the damage is the same one that fatigues every material on the surface. Watch now at the scale of a single SEAL. Heat gives the long molecular chains inside a polymer SEAL energy, and in some materials the softening lets the SEAL ooze slowly out of the groove, holding it in place, the way toothpaste inches out of a tube left too long in the sun. Cold takes that energy away. The same cold that drops the surface to 173 degrees below zero every lunar night pulls those chains tight, and they stiffen and contract, and the SEAL shrinks back from the surfaces it was pressed against, opening a gap too small to see. That cycle repeats every 29 days. Warm, cold, for as long as the habitat stands. Each cycle adds a little more fatigue. Eventually a crack starts. It may never grow large enough to notice by eye. It does not need to. A network of fractures too fine to inspect is enough to let air find its way out. Engineers reach for better materials to slow this down. PTFE, a slick, chemically stubborn plastic, resists most of what would corrode a lesser SEAL, but it is exactly the material prone to that toothpaste-like ooze under sustained pressure. Indium, a metal soft enough to dent with a fingernail, presses into gaps and conforms beautifully, but takes a permanent set after enough cycles and never springs back the same. Every option trades one weakness for another. And here is the part nobody can currently answer. The seals flying today, the best the ISS has, work in a gentler regime, stable temperatures, quick replacement, low Earth orbit. None of them has ever been tested against the full lunar combination, the 300-degree swing, the abrasive dust, the accumulated radiation, all acting on the same material at once for years. Laboratories can simulate any one of those stresses on its own. No facility on Earth can simulate all of them together, for the length of time a permanent habitat would need. So the honest answer is that nobody knows how these seals behave under real lunar conditions over real lunar timescales. Not a gap in the modeling that a few more years of research will quietly close. A genuine unknown, the kind a permanent settlement would have to be built standing on. Push the 99% number further out and the picture only gets worse. Give each of 1,000 seals a very optimistic 99.99% chance of surviving any single year. After 1 year, the odds that every seal is still holding sit around 90%. After 10 years, that drops to 37%. After 25 years, it falls below 10%. And that assumes no shared weakness across the batch, no manufacturing flaw, no stress nobody predicted, all of which would make the real number worse, not better. The obvious response is redundancy. Build backups into every seal, every joint, every hatch, so no single failure can open the habitat to vacuum. But here's where it gets strange. Every redundant seal is one more seal that can fail. Doubling the seals does not remove risk, it multiplies the number of things that can go wrong, even as it lowers the odds that any one failure turns catastrophic. And redundancy is never free. Every extra interface needs its own seal. Every backup needs its own monitoring, its own maintenance schedule, its own training for a crew already stretched thin. The habitat grows larger, heavier, more expensive and harder to manage, until the complexity itself becomes a new kind of risk. One measured not in a single point of failure anymore, but in how many people and procedures it takes to watch over all the new points at once. Not a solution. A trade, one form of failure exchanged for another. And that trade only covers the seals that hold still. The parts built to move, the hinges, the latches, the pumps that never stop turning, face a different kind of wear entirely. A pressure hatch shows the wear plainly. It has to do two things at once, and both are hard. Closed, it has to seal completely, pressing flush despite manufacturing tolerances, thermal warping, and whatever dust has settled on the sealing surface since the last cycle. Open and closed, it has to move, again and again, for years, through a hinge with no liquid lubricant to smooth the motion. A latch that has to catch cleanly every time, an actuator that has to work across a swing of hundreds of degrees. Every one of those is a place things go wrong. In vacuum, with no oil film between them, a hinge pin rubs directly against its bushing, metal on metal. That contact does something specific over time, a process called galling, where the two surfaces effectively weld together at a microscopic scale, and then tear apart again with every movement, ripping small amounts of material loose each time the joint swings. The hinge does not fail all at once. It stiffens, it roughens, eventually it binds. Latches gather dust in their working parts and start to jam, or scratch a groove into a seal that used to hold air perfectly. And every one of those small injuries is permanent. There is no sanding it smooth again with what a small crew happens to have on hand, no foundry down the road, no replacement bushing waiting in a supply closet. Whatever wear a joint accumulates this month, it carries into next month, and the month after that. On the ISS, astronauts already log hatch mechanisms as needing regular attention. Some have grown stiff and temperamental over the station's 2 decades in orbit, and that is with routine maintenance, lubricants formulated for space, and a resupply chain able to launch a replacement part when one is genuinely needed. A lunar habitat gets none of that margin. The hatch installed in year 1 is very likely the hatch still in service in year 20, stiffening, roughening, binding a little more with each open and close. The same is true of every pump, valve, actuator, motor, and fan running anywhere in the habitat. It is tempting to picture the danger here as a single dramatic moment. A rupture, a blowout, an alarm cutting through the quiet. That is not how this kind of system usually fails. Not a rupture. A slow, invisible accumulation. A filter losing capacity by degrees. A catalyst quietly poisoned. A room slowly filling with smoke nobody notices until they are already coughing. Human metabolism alone produces a small chemical fog, acetone, isoprene, alcohols, aldehydes, ammonia, hydrogen sulfide, the mix shifting with diet, stress, and health. The walls, the coatings, the adhesives holding everything together off-gas their own volatile compounds. Electronics produce ozone simply by running. Cleaning agents leave residue behind after every wipe down. None of it is designed for. The systems built to scrub carbon dioxide and manage humidity were never meant to catch this second, quieter mixture, and it accumulates anyway. Filtration has real limits. Activated carbon absorbs organic compounds well, until it does not. Once its capacity is used up, it stops working, and under the wrong conditions, it can release what it already trapped back into the air the crew is breathing. Catalytic oxidizers break down some of these compounds chemically, but they are poisoned by silicones, halogens, and heavy metals, and once poisoned, the catalyst has to be replaced with a part that may not exist anywhere on the moon. Particulate filters miss the very finest grains entirely, so those stay suspended, and every breath draws some of them in. The ISS already offers a preview. The station has recorded episodes of elevated carbon monoxide, elevated ammonia, elevated formaldehyde, tracked by sensors watching for dozens of compounds and filters swapped on a strict schedule. Even managed that carefully, the air inside smells distinctly of machine oil and plastic in closed rooms, not like anything outdoors, and some crew members report headaches, some report nasal congestion. On Earth, this has a name, sick building syndrome, and it has a cure. You leave the building. On the moon, there is no building to leave. Every breath, for years, comes from the same recycled, accumulating mixture. Water carries the same quiet arithmetic. The ISS water recovery system turns urine, humidity condensate, and wastewater back into something drinkable, filtered, distilled, oxidized, and it recovers more than 90% of what goes in. But the fraction it does not recover is not simply lost. It concentrates. Minerals build up in the leftover brine. Organic compounds resistant to oxidation accumulate. Biofilms take hold in the plumbing despite every antimicrobial treatment thrown at them. The system needs its distillation units replaced as scale eats their efficiency. Its filter beds swapped once they saturate. Major overhauls at intervals across its working life. A lunar system faces every one of those same demands with none of the ISS's options. No fresh distillation unit waiting on the next cargo flight, no spare filter bed a few weeks away. And the waste it concentrates does not disappear. There is no drain to send it down, no truck to haul it off. It sits in storage, growing, one more inventory the habitat has to carry for as long as anyone lives inside it. The proposed answer to a shortage of water is ice, buried in craters near the lunar poles that sunlight has never reached. It sounds like relief. It is not. Those permanently shadowed craters are among the coldest places anywhere in the solar system, down near 250 degrees below zero, colder than the surface of Pluto. Lubricants that flow at ordinary lunar day temperatures freeze solid. Metals that flex on the sunlit surface turn brittle in that shadow. Electronics built to survive a 300-degree daily swing meet an entirely different regime here. A cold that never breaks. And the ice itself is not clean. It is bound into the regolith, mixed through mineral grains, carrying volatiles trapped there for billions of years. Carbon monoxide, hydrogen sulfide, ammonia, and stranger compounds besides. Pulling it free means drilling into frozen ground harder than concrete. Then running it through processing equipment that clogs with the very contaminants it exists to remove. The machines built to solve the water problem are themselves degrading in one of the harshest environments the moon has to offer. Not a clean source outside the loop. The same loop, reaching one crater colder. Every one of these failures so far has belonged to hardware. Metal, polymer, filter, seal, hinge, drilling bit. But none of it runs itself. Somewhere inside all this slowly poisoning air and slowly concentrating water are the people it is meant to keep alive. And their own bodies turn out to be a closed system with failure modes of their own. That is not a metaphor. It has already been tried once, under conditions built to be about as forgiving as a closed loop could ever get. The year was 1991. 8 researchers sealed themselves inside Biosphere 2, a 3.14-acre structure of glass and steel in the Arizona desert, roughly the footprint of 2 football fields under a single connected roof. People called it a greenhouse cathedral. Inside were a miniature rainforest, a coral reef, a savanna, a marsh, farmland, and living quarters, stocked with close to 5,000 species chosen to hold each other in balance. Every one of those species had a job. Plants would scrub the air, natural processes would clean the water, crops grown inside would feed the crew. Nothing was meant to enter or leave once the doors sealed. No outside air, no outside water, no truck idling nearby with more food. The idea reached past Arizona. If 8 trained, motivated people could live for 2 years sealed off from the outside world, breathing air their own garden produced, and drinking water their own swamp purified, it would prove that closed-loop living itself worked, and that humans belonged on the moon or on Mars. Within 16 months, it had already come apart. Oxygen inside the dome fell from 21% to 14%, air as thin as the air above 13,000 feet, higher than most mountain base camps. Nobody had modeled a drop that steep. The soil inside was consuming oxygen faster than the plants could replace it, a chemistry problem nobody on the design team had weighted correctly. Researchers grew fatigued. Some developed sleep apnea. Cognitive tests slipped. Simple arithmetic took longer. Conversations lost their thread. Eventually, technicians standing outside the dome had to pump oxygen back in by force, which meant the experiment had quietly stopped being closed at all, well short of the 2 years the project had planned to run. The crops underperformed too, month after month, and hunger became a daily condition rather than an occasional one. By the end, the average researcher had lost 16% of their body weight, enough that clothes stopped fitting and faces changed shape. But the failure that mattered most was not chemical. It was human. These were not random volunteers. They were expert researchers who had chosen this life and understood exactly what the project needed from them. And still, the 8 split into 2 factions of 4. They stopped speaking to each other. Scientific collaboration, the entire stated purpose of the project, broke down between people who now ate, slept, and worked a few dozen feet apart while treating one another as strangers they shared a roof with. Confinement did that. Constant exposure to the same small group did that. And watching a carefully designed world fail around them, slowly, in plain view, did the rest. A system that closed perfectly on paper did not survive contact with the people living inside it. Here is what makes that outcome worse than it already sounds. Biosphere 2 held nearly every advantage a closed system could ask for, and it still came apart. It sat in temperate Arizona, so when climate control faltered, the result was discomfort, not death. A lunar habitat facing the same kind of fault meets a 300-degree swing and vacuum on the other side of the wall. A failure that kills within hours, not one that sends you looking for a sweater. Biosphere 2 was also surrounded, on every side, by an ordinary breathable atmosphere. When its oxygen crashed, technicians simply opened a valve and pumped more in from outside. The moon offers no outside air to draw on. A failed oxygen generator there leaves a crew with exactly what sits in their own tanks and nothing else. And Biosphere 2 kept an emergency exit the whole time it ran. Any of the 8 could, in principle, have walked out the door and ended the experiment on the spot. The moon's only exit is a spacecraft that may not be fueled, a launch window that may not align, and a 3-day transit a sick or injured person may not survive. Then there is scale. Biosphere 2 gave its 8 occupants 3 acres to spread out across, Gardens and marsh and farmland enough to put real distance between yourself and a person you had stopped speaking to. A walk to the savannah or the coral reef could function as a kind of escape, even inside a sealed structure. Lunar habitat designs on the table now run to a few thousand cubic feet, not much more room than a modest house. There is no marsh to disappear into, no rainforest wing to sit in alone for an afternoon. 8 people with 3 acres between them still ended up hating each other. What happens to 6 people sharing a few thousand cubic feet, for years instead of months, with nowhere farther left to walk? The lesson underneath all of it is simple, and it changes how everything before this point should be read. Humans are not cargo that closed-loop life support merely protects. They are active parts of the system, and unpredictable ones, at once its entire purpose and its least reliable component. A seal either holds pressure or it does not. A catalyst either converts a gas or it does not. A person under years of confinement, thinning air, and the same few faces at every meal does not fail in so clean a way. Every engineering problem already described, the seals, the filters, the catalysts, the dust working its way into every seam, gets a person added on top of it now. Someone who needs to sleep, who reacts badly to isolation, whose judgment can slip under strain in ways no material scientist has ever had to model. Not proof that people can live inside a closed loop. Proof that they barely can, under the gentlest version of that test the Earth is able to offer. Biosphere 2 answered one question and opened a harder one. It showed that even the softest version of this experiment breaks down under its own weight, with survivable air outside the wall, an ordinary climate, and a door that always opened. What it never had to answer is what the hostile version does to the body itself, not just to patience and temperament, but to blood, bone, and cell. Over years spent somewhere, the human body was never built to survive. That reckoning was still ahead, and it would not be gentle. Start with the plainest fact in that reckoning. A human body is not built for this place, and it keeps a precise running account of every hour spent inside it. On Earth, the atmosphere and the magnetic field do a job so complete that most people never think about it. Cosmic radiation gets filtered down to background levels, the body shrugs off without effort. A dental X-ray adds almost nothing. A transatlantic flight adds almost nothing. The moon offers no such filter. Its atmosphere does not exist. Its magnetic field is a memory of a core that solidified billions of years ago. Every galactic cosmic ray that has been racing toward the moon since it left some dying star arrives exactly as violent as when it started. Not filtered, not deflected, arriving whole. These rays are heavy nuclei, often iron, moving near the speed of light. When one strikes tissue, it tears through cell after cell, breaking chemical bonds and cutting into strands of DNA along its path. That is the background hum of lunar radiation, constant and largely silent. The acute version arrives without that patience. A coronal mass ejection can hurl billions of tons of charged particles outward from the sun, and depending on the geometry, that storm can reach the moon within minutes to hours. A crew caught without shelter can absorb a dose large enough to cause acute radiation syndrome. Nausea first, then immune collapse. At the extreme end, death within days. Piling mass in front of the body sounds like the obvious fix, and it is not that simple. The same shielding paradox that complicates every electronic system complicates flesh too. Heavy, dense material can multiply the spray of secondary particles reaching whatever sits behind it. So more shielding does not always mean less exposure. Hydrogen-rich material, water, plastic, does better. The most effective barrier would be several meters of regolith piled over the habitat, but burying a structure at that scale requires construction capability nobody currently possesses. So residents live with whatever practical, partial shielding a real mission can actually build. Even the best of that only reduces the dose. It does not erase it. Here is what that dose actually adds up to. Studies of realistic near-term habitats put the lunar surface dose at roughly 60 to 80 millisieverts a year. That is 10 to 20 times the average person's yearly exposure on Earth, and 2 to 3 times what an astronaut absorbs aboard the International Space Station. NASA's current safety standard tries to keep an astronaut's added lifetime cancer risk below 3%. At lunar levels, A resident reaches that ceiling within a handful of years. Stay a decade, and the dose runs far past any limit anyone currently considers acceptable. Not a spike to recover from. A constant compounding cost with no discount for good behavior. Cancer is the part of the ledger with numbers attached to it. The rest is murkier, and in its way, more unsettling. Long-term exposure is linked to cardiovascular disease and cataracts. Cognitive decline shows up in the data too. Animal studies suggest memory loss and behavioral change from the same heavy ion radiation that dominates the lunar environment, and some researchers suspect the central nervous system is unusually vulnerable to exactly this kind of particle. Nobody can say for certain, because no population has ever absorbed this much of this particular kind of radiation for this long. The only real precedent available is the International Space Station, and even that precedent is thinner than it looks. Astronauts there stay for months, not years, and they orbit low enough that Earth's own magnetic field still catches a share of what would otherwise reach them. Take that partial shield away, stretch the exposure from months into years, and there is no longer a comparison to lean on. Some lunar proposals go further still, describing children conceived and raised entirely inside that radiation environment, their whole development spent somewhere human biology never evolved to withstand. That is not a plan with a known outcome. It is a wager placed against odds nobody can calculate. Radiation is only the first way the moon makes the body more fragile. Isolation is the second, and it turns every other injury into a much larger problem. Spaceflight has always kept one guarantee in reserve. An astronaut on the International Space Station with appendicitis, a heart attack, or a serious injury can be brought back to Earth within hours. That guarantee does not exist on the moon. Getting a patient home takes days at minimum. Transit alone runs about 3 days, and only if a fueled spacecraft happens to be ready, the launch window happens to align, and the patient can physically survive the acceleration, the vibration, and the re-entry that follow. Not hours, days, and only under ideal conditions that will not always hold. Many emergencies do not grant 3 days. A ruptured appendix does not wait. A cardiac event does not wait. Internal bleeding from a fall or an equipment accident does not wait. Each needs intervention within hours, sometimes minutes, and no lunar evacuation plan moves that fast. So a habitat has to carry medical capability that would rival a hospital, not because it is well funded, but because nothing weaker survives contact with reality. Capability, though, is not just a cabinet of equipment. It is skill kept sharp through use, and supplies kept fresh through turnover, and both erode in a place this isolated. A surgeon on Earth might perform hundreds of procedures a year and stay practiced without trying. A lunar surgeon might perform one, or none. Skill fades without repetition, the same way any other capacity does. The equipment ages in parallel. Imaging systems drift out of calibration, monitors need verification nobody nearby can easily provide, and a CT scanner exposed to years of the same radiation it is meant to detect can start returning images nobody should trust. Sterile technique depends on supplies too. The wraps, the solutions, the disposable instruments that a hospital reorders without a second thought, and none of that arrives on the next truck the way it would on Earth. Medicine expires too. Every drug carries a shelf life, and a habitat cannot stock unlimited quantities of everything forever. Sooner or later, a needed medication has degraded past use, or was never carried at all, and the choice that follows is not really a medical choice anymore. It is decided by whatever happens to be on the shelf. The body keeps this account whether anyone reads it or not. Radiation dose climbing, medical capability quietly thinning, no way to close the ledger early. What years of that same isolation do to the mind was a separate question, and a harder one, still waiting to be asked. The mind keeps its own kind of ledger, and it does not wait for the body's account to close before it starts. On Earth, a strained mind finds relief in change, a walk under different light, a weekend away, a conversation had face to face. A lunar habitat offers none of that relief, because it offers no change at all. Humans evolved as social creatures inside a world that never stops shifting. Seasons turning, weather changing, faces new and old, ground that varies from valley to ridge. A lunar habitat gives none of it. The same small pressurized volume, the same handful of people, the same view through the same window, grey regolith under a black sky, craters that do not move, a stillness that does not break. Earth rises and sets overhead on a 2-week cycle, but otherwise nothing marks one day from the day before it, and nothing marks a season, because there are no seasons to mark. Most of the day is not spent on the science that drew anyone there in the first place. It is spent on filter changes, seal inspections, calibration checks, inventory counts, the unglamorous work of keeping complicated machinery alive. That work fills the hours the mission was supposed to be about, and it repeats. Confinement like this carries a documented cost, gathered from decades of expeditions and simulated missions here on Earth. Isolation breeds friction, small habits growing unbearable at close range, monotony flattens mood, motivation eroding as one day loses its edges against the next. Circadian rhythms tuned to a 24-hour Earth day drift under artificial light with no true dawn. Focus, memory, the ability to solve a problem nobody has seen before, all measurably decline the longer a mission runs. The International Space Station offers the closest comparison, and even it is a gentler test. Crews rotate every 6 months, screened in advance for compatibility, trained specifically in resolving conflict, given a return date fixed on the calendar before they ever leave the ground. Even with all of that, tension still builds, small irritations, disagreements over shared resources, and mission psychologists work constantly from the ground just to keep a 6-person crew functioning for half a year. A lunar resident gets none of those cushions and stays far longer. Every word exchanged with Earth carries a delay of 1 to 1.3 seconds each way, small enough to miss and large enough to break the rhythm of an ordinary conversation. You speak, you wait, a reply arrives that already feels slightly behind the moment it answers. That small gap sits inside every call home, for as long as the mission lasts, and the mission itself has no fixed end. Return is not a date circled on a calendar. It is a complicated, expensive operation that can slip or be cancelled for reasons the crew does not control. The one thing that carried ISS crews through 6 months, a known day when it ends, does not exist here. Biosphere 2 already showed what that unraveling looks like. 8 researchers who began the project united in purpose split, within months, into 2 factions that stopped speaking to each other. Cooperation broke down, maintenance broke down with it, the same careful attention that kept air and water cycling falling away as conflict ate the hours it needed. But here is where the psychology and the machinery start feeding each other. Lunar systems need continuous, careful attention. A missed inspection today becomes a leak next month. A skipped filter change lets contamination build past the point of easy correction. An ignored warning becomes a failure. That attention has to come from people who are tired, low, possibly in conflict, running the same checklist in the same room for months or years running. Under those conditions, the errors are not exotic. A seal seated wrong, a reading copied down incorrectly, a calibration skipped, because it was skipped last week too, and nothing happened that time. A warning waved off by someone who has heard that alarm cry wolf before. Fatigue raises the error rate. Stress narrows what a mind notices. Conflict breaks down exactly the communication that keeps a crew safe. Industrial accident investigations find this pattern again and again, which is why organizations that cannot afford failure spend heavily on the welfare of the people doing the work. A lunar crew has almost none of those tools. No trip away to reset. No change of scenery. No visit from someone outside the loop. Nowhere to go. Because leaving the habitat means leaving the only breathable air for hundreds of thousands of miles, in every direction. Rotating the crew looks like an answer. Spreading the strain across more people, fresh arrivals replacing those who have been worn down. Not a solution. A trade, one cost exchanged for another. Flying a new crew up, training them, flying the old crew home, could run to billions of dollars each time it happens. Every installation also accumulates its own quirks, its own workarounds, procedures nobody wrote down because everyone on site simply knew them. A new crew arrives without that knowledge. The crew leaving is already thinking about home, not about handing over what they know, not a clean transfer, a gap, right at the moment the system can least afford one. Keep the same crew in place longer instead, and the opposite problem builds. Stress, monotony, and friction accumulate without a break, and maintenance performance slides exactly as those pressures mount. Neither answer escapes the trap. Rotate the crew, and the cost is money and a dangerous handoff. Keep the crew, and the cost is years of compounding strain. Automation sounds like the way around both options, machines instead of exhausted people running the checklists. Automation is already part of any real design, monitoring the environment, handling routine adjustments, logging what needs to be tracked, but it has its own limits. Sensors drift, actuators jam. Software meets a situation nobody anticipated and does not know what to do with it. Automating a task does not remove the maintenance it requires. It moves the maintenance onto the automated system, one more layer standing between the crew and the moment something actually needs fixing. And the same environment already picking apart every other piece of electronics. Radiation flipping memory bits, dust jamming actuators, heat and cold stressing components, picks apart the robots too. They get no exemption. Automation is also weakest exactly where a lunar habitat is strongest at producing trouble, the failure nobody designed for. The combination of small problems that adds up to something new. A human mind still does something no algorithm on the moon can match. Notice what looks wrong, improvise past a checklist that does not cover this case. And there is a simpler reason automation cannot solve this at all. Strip the people out entirely, and the habitat could still hum along, air cycling, water recycling, systems running for no one. Not a colony anymore, a robotic outpost with the lights left on. The whole point was always the people inside it, and that same presence, fragile, distractible, exhausted, is not a flaw waiting to be engineered away. It is the reason any of this exists in the first place. The body keeps its ledger, the mind keeps its own. And a worn mind, checking a seal it has checked 100 times before, is exactly where the two ledgers meet. That worn mind, checking the same seal for the 100th time, is not a thought experiment. It is where a chain reaction actually starts. Complex systems rarely fail all at once. They fail in sequence. One component weakens, and the weakness leans on its neighbors. Those neighbors carry a little more load, degrade a little faster, and pass the strain further down the chain. Not one failure, a chain of them, each one leaning its weight onto the next. Failures propagate through a system faster than repairs can contain them. A minor problem becomes a major one connected breakdown at a time. On the moon, where nothing is redundant enough and nothing arrives in time, that chain is especially dangerous. Picture the smallest possible start. A micrometeorite strikes a module's outer shell and punches a hole about 2 millimeters across, smaller than the tip of a pencil. Vacuum does not forgive a hole that size. Air begins leaving through it steadily, the pressure gauge sliding down. The pressure system notices first. It answers the way it is built to answer, running the pumps harder, pushing oxygen generation up to hold the cabin steady. The crew starts the breach search, working a grid pattern room by room while the system buys them time. But the hole sits behind a rack of equipment that has to be unbolted and moved before anyone can see the wall behind it. The search runs long, and while it runs long, a pump that has been working harder than it was designed for starts to fail on its own. A bearing that should ride on a film of lubricant begins to grind metal against metal. The motor pulls more current to compensate. A sensor reads the rising heat and does exactly what it is built to do. It shuts the pump down to protect it. Now the system runs on fewer pumps, and the ones still working carry more load, and someone has to stop searching for the hole to go diagnose the pump instead. One problem has become two. The crew hunting for a hole in the hull is now a crew short. The air itself starts to drift. Oxygen generation, tuned for a stable cabin, behaves erratically under fluctuating pressure. Carbon dioxide scrubbing loses efficiency. And the crew, without quite noticing why, starts to get headaches. Concentration slips. That is not fear. That is chemistry, a mild fog settling over the exact minds trying to solve the problem. Stressed. Behind schedule, breathing air that is quietly turning against them. Under those conditions, the patch goes on wrong. It holds at first, but the seal underneath it is imperfect, and within weeks it will need doing again. Nothing in that chain required bad luck stacked on bad luck. A micrometeorite strike is routine. A pump bearing failing under stress is routine. A tired crew making a small error under pressure is routine. Not one exceptional event. A sequence of ordinary ones, each following logically from the one before, adding up to a crisis that no single failure, alone, would have caused. And the odds of that sequence do not stay fixed. New equipment operates well inside its margins, and a stress that would trigger a cascade in year 10 barely registers in year 1. But equipment ages, tolerances shrink, and the same trigger that a fresh system would absorb without comment becomes, for a worn one, the first domino. A seal with a little life left in it flexes and reseats. A seal near the end of its life cracks. Crews wear down too across a mission, in their own way. Rested and alert, people catch a warning early and answer it calmly. Tired and frayed, the same warning gets missed, or answered late, or answered wrong. Every year that passes without total collapse adds wear to the hardware and fatigue to the people running it. And the probability of the next cascade climbs quietly in the background the entire time, waiting for the trigger that finally exceeds what a tired crew and worn hardware can still absorb. Here is the harder truth underneath all of it. Every system in that habitat, the pumps, the scrubbers, the shielding, the heaters, exists for exactly one reason: to keep a small number of human bodies alive. Strip the humans out and none of it needs to exist at all. But those same humans are also the least cooperative part of the machine. They breathe air and drink water and eat food, and draw power on a fixed biological schedule that does not negotiate. They generate waste. They need a narrow slice of temperature and pressure to function at all. And they get tired, and they get sick, and they make mistakes exactly when the mistake costs the most. A robotic outpost could, in principle, run for decades on very little intervention. Machines tolerate wider swings of heat and cold. They need no air, no water, no food. They feel no stress, and when they fail, they do not turn a mechanical problem into a human tragedy. A habitat built around living people carries none of that patience. It has to meet human needs perfectly, continuously, for years or decades running, so a gap a robot would absorb without comment is, for a person, an emergency. The people are not a design flaw waiting to be engineered away. They are the entire reason the habitat exists in the first place. And that is exactly why the closed loop failing matters as much as it does. Take the humans out and the degrading systems become a curiosity, mildly interesting hardware slowly running down on an empty world. Put them back in, and the same slow decline becomes the only thing that matters. Every argument made so far, the vacuum, the heat, the radiation, the dust, the leaking recycling, the failing seals, the exhausted minds, keeps arriving back at this same wall. It is worth asking finally what that wall actually is. 70 years of a much gentler place on Earth already answers part of it. In 1911, the Norwegian explorer Roald Amundsen became the first human being to stand at the South Pole. He got there through meticulous planning and one governing priority that shaped every choice along the way: getting his team home alive. He brought sled dogs that could be slaughtered for food on the return leg, cached supplies along the route, and calculated margins for weather and error. He never intended to stay. He planted a flag, took his measurements, left a tent and a letter for his rival, Robert Scott, and turned around. Within weeks, the wind had buried every trace of him. More than a century later, humans still have not solved the problem of staying. Since the International Geophysical Year of 1957, nations have kept research stations running across the continent. McMurdo Station, run by the United States, has grown into a small settlement housing over 1,000 people through the austral summer, with its own power plant, water treatment, a clinic, workshops. The Soviet Union, and later Russia, has held Vostok Station near the geomagnetic pole since that same year, enduring some of the coldest air ever measured on Earth, minus 89.2 degrees Celsius in 1983, cold enough to freeze carbon dioxide out of the sky. Researchers there drilled through kilometers of ice to reach a lake sealed underneath it for millions of years. These are genuine achievements. And still, no one is born at McMurdo. No child grows up at Vostok. No family has built a life across 2 generations on that ice. People serve a season or a year and leave. Not a colony, a rotation. The permanent population of Antarctica, after 70 years of well-funded, technically excellent effort, is 0. The reason is resupply or its absence. Antarctic stations survive because ships and aircraft keep bringing food, fuel, parts, and fresh people, and keep hauling away the waste. McMurdo alone burns millions of gallons of fuel a year, shipped in and unloaded during a narrow summer window. If the ship stopped, the station would go dark within a season. Food arrives the same way, because Antarctica grows nothing to eat. Its largest native land animal is a wingless midge, less than half an inch long. Equipment fails constantly in the cold, and spares flow in from warmer places without pause. And this is Antarctica. The air is breathable. The cold is survivable in the right clothing. Pressure is ordinary. Radiation is background, nothing more. A sick researcher can usually still be flown out. The moon removes every one of those things. Antarctica's temperature swings across roughly 100 degrees, record cold to summer days above freezing. The moon swings 300. Antarctic buildings hold ordinary pressure against ordinary pressure outside, so a cracked window is an inconvenience. A lunar habitat holds a full atmosphere against nothing, close to 10 tons of outward force on every square meter of hull, roughly a loaded delivery truck balanced on 1 square floor. A cracked window there is a countdown, where an ill researcher reaches Christchurch in hours by aircraft. A lunar resident waits for a ship, then survives days of transit, and hopes the injury allows for the wait. So the question worth asking plainly is this: if 70 years of money and genuine skill have not made Antarctica self-sufficient, on a continent this much gentler, what makes the moon different? The usual answer, spoken or not, is faith. Faith that seals will stop degrading. Faith that filters will stop clogging. Faith that robots and mining and biology will eventually close every gap. That faith fails for a reason worth stating plainly. Some problems are not awaiting a clever enough engineer. They are thermodynamic. The second law of thermodynamics says that in a closed system, disorder always increases. Organization decays. Structure breaks down. This sits beside the conservation of energy and the speed of light, and is one of the fixed boundaries of physics. A lunar habitat, for practical purposes, is a closed system. Energy arrives from the sun or a reactor. A little mass arrives through resupply, but almost nothing leaves, and almost nothing extra comes in. Earth is different. It draws endlessly on resources accumulated over billions of years, and dumps its disorder into a space large enough to absorb it. So the loop there never really closes. On the moon, the loop closes tight. What you brought, or what you pull from the ground with machinery that is itself wearing down, is what you have. Waste has nowhere to go. Every inefficiency stays inside the system and adds to the next one. Entropy does not announce itself. It wins slowly. Seals stiffen, filters saturate, catalysts poison, bearings wear, electronics take radiation damage they cannot repair. None of it can be stopped, only slowed, and slowing it costs energy and materials that carry their own thermodynamic price. Holding a complex system together against decay requires a constant supply of order from outside. Fresh parts, fresh materials, fresh capacity. On Earth, that supply is so easy, it is invisible. On the moon, it is scarce by definition. Even the sunlight is unreliable, abundant for 2 weeks and gone for 2 weeks, and the batteries and fuel cells built to bridge that gap fade and consume themselves with every cycle. There is no water cycle, no carbon cycle, no nitrogen cycle quietly doing this work for free. Every loop on the moon has to be built from nothing and defended forever. Efficiency can rise. It cannot reach 100%, and the gap that remains is exactly where the entropy accumulates. The International Space Station gives the clearest real number for what this costs. Even in an environment gentler than the lunar surface, spared the worst radiation, cycling only tens of degrees instead of hundreds, free of dust and landing stress. Its 30-year design life has depended on continuous maintenance and thousands of tons of resupply from Earth. Left alone a single year, it would not survive. The most optimistic projections for a lunar habitat imagine handling 90 to 95% of its needs locally, an achievement nobody has demonstrated. Even at that best case, the remaining 5% still means thousands of tons shipped across 250,000 miles over decades, and 95% is the hopeful number. The station managing the job right now recovers about 90% of its water and generates its own oxygen, but still needs constant resupply of food, spares, and consumables, landing its true closure closer to 50 or 60%. A full closed loop, 100%, fails for a deeper reason. The machines meant to manufacture replacements are complex systems too. A printer that makes spare parts needs its own spare parts. A refinery pulling metal from the ground corrodes and clogs like everything else it was built to fix. The tool that maintains the system needs its own maintenance, and eventually the layers run out. Even on Earth, with a planet-wide web of factories refined over centuries, no single facility makes everything it needs. A handful of people on the moon cannot replicate that web. The habitat will always depend on Earth for something, which means it is never truly permanent. It enters decline the moment that supply line is interrupted by a funding cut, a war, a change of government, an economic crisis 250,000 miles away. The reliability mathematics, run now across the whole system rather than one component, says the same thing in numbers. Picture 100 critical systems, each with a 99% chance of surviving any given year, already an optimistic assumption. The odds all 100 survive that single year come out to about 37%. Raise each system's reliability to 99.9%, extraordinary by any standard, and the odds all 100 survive 1 year rise to about 90%. Run those same systems for 10 years, and the number falls to about 35%. Redundancy softens this, but every backup is one more thing that can itself fail, so it never erases the arithmetic. Given enough time, every system fails. Given enough failures, some cannot be repaired. Given enough unrepaired failures, the habitat stops being livable. That is not pessimism. It is actuarial math, run honesty. Closed-loop life support degrades faster than it can be maintained. It was true of the seals. It was true of the filters, the catalysts, the tired minds checking them. And now, measured against 70 years of the gentlest version of this problem Earth has to offer, and against a law of physics that permits no exception, it stops being one claim among many and becomes the verdict the whole argument has been building toward. What remains is the question of what to do with that verdict and what the moon might still be worth. Once staying is no longer the goal. The case is made. What is left is not another argument but a choice about how to see the moon once staying stops being the point of looking at it. Before that choice can settle, though, 3 objections deserve a straight answer, because each one sounds reasonable on first hearing. The first is survival. If an asteroid, a supervolcano, a pandemic, a war, a runaway machine intelligence, or a changing climate could end human civilization on Earth, shouldn't a second world hedge the bet? The instinct is sound. The conclusion is not. Wanting to survive does not make a seal last longer, a filter clog less, radiation weigh less on tissue, or dust turn less abrasive. Motivation is not physics. A colony built to save humanity would need to be simpler and hardier than the civilization it replaces. The way a lifeboat is simpler and hardier than the ship it is lowered from. A lunar colony is not that. It is far more fragile than Earth, and it depends on Earth for nearly everything. Air, water, spare parts, expertise, food. If Earth were ever damaged badly enough to threaten the colony's supply lines, the colony would not rescue anyone. It would simply add a smaller, harder death to the larger one already underway, not a lifeboat. A second casualty, further from help. The second objection reaches for technology not yet built, nanotechnology that repairs itself, an artificial intelligence patient enough to manage endless complexity, materials immune to fatigue, fusion power without limit, biology engineered to recycle waste perfectly. Perhaps some of this arrives one day, but a plan resting on inventions that do not exist yet is not an engineering plan. It is a hope wearing an engineering plan's clothes, The seals degrading right now, the filters clogging right now, the catalyst poisoning right now are documented across decades of actual spaceflight, not decades of speculation. And even the imagined technologies would still answer to the same law. A self-repairing machine still needs energy and material to do the repairing. An intelligence, however vast, cannot talk metal out of fatiguing or a radiation dose out of accumulating. A fusion reactor still needs a containment vessel, and containment vessels corrode. The third objection is economic. Mining, tourism, commerce. The argument that money will chase the problem until money solves it. But incentive is not capability. A business model can accelerate a solution that physics already allows. It cannot manufacture one that physics forbids. And here is the detail the objection quietly skips over. None of that economic activity actually requires anyone to stay. Lunar mining can run on rotating crews the way offshore oil platforms do. Workers arriving for a tour, leaving before the rig or the body wears out. Lunar tourism can be a visit, not a residence. Which raises the real question underneath all three. If the moon cannot be a home, what is it actually for? The honest answer is that it is genuinely valuable, just not in the way the brochures imagined. Its far side, shielded from every radio signal Earth produces, is an unmatched listening post for the faintest sounds in the universe. Its permanently shadowed craters may hold ice laid down since before Earth had continents. A frozen record of the early solar system nobody has read yet. Its untouched surface preserves geological history that Earth's restless crust erased long ago. Its water ice could become rocket fuel for missions farther out. Its regolith holds aluminum, iron, titanium, and possibly helium-3, worth something if fusion power ever becomes ordinary. None of this needs a family living there. It needs robots running routine operations and rotating crews arriving when their hands are worth more than a machine's, then going home. We have already made this adjustment once before, at the bottom of the world. Nobody grieves that Antarctica has no schools, no birthdays, no second generation growing up on the ice. We treat it as a place worth visiting and worth protecting, not a place worth settling. And that framing lets us take everything valuable from it without demanding it become something it was never going to be. The moon can occupy the same place in the imagination. Not a home, a workplace, a frontier, a laboratory with the lights left on. There is a deeper reason this reframing is right, and it has nothing to do with engineering. Humanity has walked out of East Africa into deserts, jungles, mountains, and the total dark of the Arctic winter, into places that would kill an unprepared body within minutes. Every one of those places still shared something with the cradle we started in. Air that could be breathed or filtered, water that could be gathered, cold that clothing and fire could answer, ordinary pressure, ordinary gravity, a sky that filtered out most of what space throws down. We have stretched the boundary of where a human can live. We have never once stepped outside it. The moon is not a stretch of that boundary. It has none of those things to begin with. Not harder. Different. Building a habitable pocket from nothing and holding it open against decay forever is not the same task as adapting to a harsh corner of a world already built to hold us. Somewhere beyond the moon, that different task might still be answered. A rotating station assembled and provisioned at a price a civilization can actually pay. Mars, with at least a thin atmosphere overhead, water within reach, and a day close enough to a human one that a body could keep time by it. A habitat built from asteroid material, designed from its first rivet for people to stay. None of that is settled. All of it stays open, on worlds that are not this one. The moon's part in that future is real, but smaller than the dream. A stepping stone, not the destination the dream once imagined it to be. None of this is defeat. A civilization that can tell the difference between an achievable goal and an impossible one is not a civilization giving up. It is one growing up. Every closed system ends the same way. Every hostile place eventually outlasts whatever was built to survive it. On Earth, when a system fails, there is still an elsewhere. Still a ground to stand on. Still hands that can work without machines between them and the air. Still, at the furthest edge, the way our ancestors lived before any of this was invented. On the moon, none of that exists. No elsewhere. No ground, only vacuum where the ground should be. No hands that last once the machines stop, only bodies that need them. No older way of living to fall back on. People will return, perhaps within this decade. They will stay days, then weeks, perhaps months, and they will learn more than 100 years of guessing ever taught anyone. And then they will come home, to the world where a filter that fails gets replaced from a civilization that makes millions of them, where a seal that leaks is not a death sentence because the air outside is breathable, where losing power is an inconvenience and not a countdown. The world we are built for, because it is the one that built us. The moon will never be a home. That is not a tragedy. It is only what is true, and only the true thing can be built on. A species that cannot keep its own world livable will not be saved by a barren one. Protecting this world is not a retreat from the stars. It is the one plan a future in space can actually stand on. The moon will go on watching, the way it has since before there were eyes to look up at it, beautiful and bare, while generation after generation wonders what it would be like to live there. They will not find out. The seals will fail. The filters will clog. The air will poison. The water will foul. Not from carelessness, and not from technology falling short, but because entropy is patient. The moon is unforgiving, and no system holds against both forever. Somewhere in that quiet, inevitable failure sits the whole of the lesson. Not what we wished were true, but what was always actually there. Still watching, still waiting, still whole.